Finding myself up in the clouds, I'm surrounded by Coldwater Sandstone. It's the dominant sandstone of the Santa Ynez Mountains that overlooks Santa Barbara. And why is it special? This sandstone unit is special in that it forms all the prominent peaks of the Santa Ynez mountain range. It also is an aesthetically pleasing sandstone unit. It's golden yellow color. Maybe it doesn't look golden yellow here. It's kind of reddish because of the oxidation or the weathering process, but on a fresh surface it's golden yellow. Due to its color and hardness and aesthetic qualities, it's prized for building homes, expensive homes, sandstone walls, and all sorts of garden features. As a matter of fact, you can travel around Santa Barbara and find it almost everywhere. This formation is believed to be about 40 million years old. Dating was done using two different methods: paleontology, which is looking at fossils. The second method was using paleomagnetism. Periodically, the Earth's magnetic field reverses, and these reversals are important in distinguishing the age of deposition. While the sediments are deposited, the iron particles or the magnetic particles within the sediment will orient themselves in accordance with the prevailing magnetic field at the time. While this formation doesn't contain a lot of iron, it does contain some. It contains enough. Both of these dating methods produce similar results, indicating that 40 million years, plus or minus, was a reasonable approximation of the age. The formation was deposited in an ocean environment. In other words, beneath the surface of the ocean, the historic, or I should say paleo-ocean. How do we know that's true? You know, we could probably look for clues and try to fact check that. Now the age part, that's a little too complicated for a simple YouTube video, but the depositional history in terms of whether it was terrestrial on land or it was marine in the ocean, you know, I bet you we could find some clues. What would we look for? Maybe we would look for macrofossils, fossils you can see with the naked eye. Maybe we'd look for ripple marks. In other words, things made by water. You could argue that both of those things happen on land, but if you can identify the type of fossil, you could probably conclude it was an ocean fossil versus a terrestrial or freshwater fossil. The ripple marks, well, that's not black and white, because yes, you get ripple marks both on land, in rivers, lakes, and in the ocean, beaches, and deeper in the ocean. So ripple marks probably wouldn't prove it was in the ocean, but ripple marks would prove it was beneath the water. What about sand dunes? They have ripple marks from air. So I guess we're just left with macrofossils. That's about as good as we can do on this trip. Let's see if we can find some. So an excellent example of bedding planes stretch up above me up to the skyline. These parallel lines represent former surfaces. When the formation was being deposited, each one of these lines would have represented the top or the daylight contact before it was in turn covered by another layer. And so the process repeats layer after layer. So once the formation becomes lithified or becomes a rock, it becomes brittle, and preferential fracture planes develop along the former bedding plane. So bedding planes become today's fracture planes. So they're easy to see in the field. Now we're going to look for some bedding planes that are exposed and see if they might have ripple marks on them. So again, you can see bedding planes. They're running up the slope away from us in parallel lines, and this giant fracture in front of me, this represents a bedding plane that is now turned into a big open fracture. So the direction of the fractures and the bedding planes is well defined. They run the same direction. So when the rock breaks, it breaks along fracture lines or bedding planes, and so it creates these big surfaces like this one right here. So what you're looking at represents a former depositional surface, meaning this was at one point the actual top of the formation. Above it was daylight, below it was formation. Today, it's part of a big mountain range. So this bedding plane surface or fracture surface represents an area that might have ripple marks. So let's see if there's some better ones. This one Appears to have possibly ripple marks, but it's deeply weathered, highly fractured and fragmented, so the evidence is pretty well obscured. Here the sandstone's rather massive. The beds must be rather thick. You don't see the discrete layers you saw back there. This is gorgeous material. It would make a fantastic wall. And look at that, a huge surface covered in ripple marks. It's also covered in climbing anchors. Apparently it makes a good climbing wall. So we found what we're looking for. These are ripple marks. These represent deposition underwater or possibly air, but there's enough other evidence to indicate this is underwater. So these ripple marks are fairly well preserved and they're abundant. They stretch all the way up, well out of the side of this camera to the top of this cliff. As you can see, the bedding planes here are very thin. You could describe these as laminae. Anyways, if you see parallel that, there's a coarser line or bedding plane. Those are shells. Those are fossilized oyster shells, clam shells, some kind of marine shell. I didn't have to go far to find an exposed shell. You can see this lighter colored material. That's the surface of the shell, and that's the inside. So this would be the shell. This would be the sand that filled the shell. Aha, more of them. So here we go. Here's some great examples of shells. They look very similar to today's marine life. This looks like a mussel shell. Even the coloration is still similar. So these are fossilized shells. 40-million-year-old fossilized shells, yes, older than even me. And look at these. Doesn't get much better than that. So the evidence is stacking up. We have lots of evidence that this is a marine formation, meaning we have ripple marks, and now we have shells.